Let's say that you're giving a gift of $10,000 on the day that you were born. And this gift is then invested into an account, some sort of a fund that earns an average annual rate of 8%, and it's compounded monthly. How old will you be when you become a millionaire from this investment? For this problem, because we're dealing with a compound interest problem, we're going to use the formula A of t equals a sub 0 times the quantity of 1 plus r over n to the power of nt. As we work through this problem, we'll ignore taxes or if there's any sort of a fee on this fund. Those things would be significant when it comes to the growth and how long it takes for you to become a millionaire, but because it's beyond the scope of this problem and for simplicity's sake, we're going to ignore taxes and fees and determine how long it will take for an investment of $10,000 growing at a rate of 8% to grow to $1 million. Let's begin. The compound interest formula that we'll use for this problem has 5 distinct parts. It begins A of t equals, A of t equals. You can think of A of t as the amount in the account after time t has passed, or the ending amount, the amount you end up with. And in this problem, we want to know how long it takes until we end up with $1 million in the account. So A of t will have a value of 1 million. A sub 0, the next quantity that I see, is the amount in the account at time 0, or the starting amount. And in this problem, we're starting with our initial amount is $10,000. Next, the value of r is the rate of growth, the percent rate of growth that this investment will grow over the course of a year. Our annual rate that we're assuming in this problem is 8%. The rate of growth is 8%. We'll represent this in the problem as a decimal. 8% is 0.08. The variable n is the number of times the interest is compounded each year. This shows up twice in the formula, once as a denominator of a fraction and another time in an exponent. Our interest will be compounded monthly, so that means the number of times that it's compounded a year is 12. N equals 12 in this problem. And finally, t stands for, of course, time. Time is measured in years, and that's what we're trying to find in this problem. Time is the unknown. The question is, at what age will you be, or how many years will pass since you are born until this investment grows to $1 million? Now that we have a value for all of the quantities in the compound interest formula, we'll simply substitute those into the formula. Substituting these values into the compound interest formula, we get an equation. 1 million equals 10,000 times the quantity of 1 plus 0.08 over 12, all to the power of 12 times t. This is an exponential equation because the variable, the unknown, t in this case, is in the exponent. Exponential equations can be solved using logarithms, and that's what we'll do to solve this equation. The first step to solve an exponential equation using logarithms is to isolate the exponential factor. I'm putting the exponential factor in a box here. I want to get this factor, this part of the equation, by itself before moving on. That can be accomplished in one step here. All I'll have to do is divide both sides of the equation by 10,000, and then that factor that has the exponent will be isolated. Dividing 1 million by 10,000 is pretty simple. We don't even need a calculator for that. 1 million divided by 10,000 is 100. And what I've also done in this step is I've taken 1 plus 0.08 over 12 and done that addition, and I've represented that with a fraction 151 over 150. This would be a repeating decimal if I would represent it as a decimal. I'm going to leave it as a fraction. the exact value of 1 plus 0.08 over 12 is 151 over 150. I've now isolated, after dividing by 10,000, I've isolated the exponential factor. The part of the problem that's raised to a power is isolated. And we can move on to step 2. Step 2 is to take the logarithm of both sides of the equation. Once the exponential factor is isolated, we're now going to take the log of both sides of the equation. Actually, we could take the log of both sides or the natural log of both sides of the equation. I'm going to choose to take the log of both sides of the equation because the log of 100 is exactly 2. Whereas if I took the natural log of both sides of the equation, the natural log of 100 would be an irrational number. However, if you're using a calculator to solve this problem, the calculator can express the answer in a very accurate way, whether you take the log or the natural log of both sides of the equation. It's not very important which you choose. Now that I've taken the log of both sides of the equation, I can do something that will make this problem a lot easier moving forward. I'm going to use the laws of logarithms to move the exponent before the logarithm. An exponential equation is difficult because the variable is in the exponent. However, once you take the log of both sides of the equation and you're dealing with logarithms, there's a property of logarithms, a law of logarithms, that states if you take the log of anything to a power, that has the same value as if you would move that exponent in front of the logarithm. The log of 151 over 50 to the power of 12 times t is the same thing as moving that exponent to the front and expressing it as 12 times t times the log of 151 over 150. And the reason that that's such a big step is because now we have an equation that doesn't have a variable in the exponent. Once you move that exponent out to the front, the variable is no longer in an exponent. The equation becomes much simpler to solve. I can solve this equation by simply using algebra to isolate the variable. What I'll do here, I want to isolate the t, so what I'll do is, first, I'll divide both sides by the big logarithm, 151 over 150. I'll divide both sides of the equation by the log of 151 over 150. And what that's going to give me is, that isolates the 12t. It's equal to a fairly complicated expression, but again, we're going to use a calculator, so this actually isn't too difficult to evaluate on a calculator. 12t equals the log of 100 over the log of 151 over 150. I haven't quite isolated the variable yet. To isolate the 12, I'll also have to divide both sides of the equation by 12. And when you divide a fraction by a number like 12, you just put that 12 in the denominator of the fraction. It's the same thing. That's the result of dividing a fraction by 12 would be to include a factor of 12 in the denominator of the fraction. And this expression represents the value of t. Now the log of 100, as I said earlier, is going to be exactly 2, but the log of 151 over 150 will be irrational. Typing this into your calculator will give you a value of, at least to 3 decimal places, 57.756 years. This is the amount of time that would pass for the $10,000 investment, compounded monthly at 8%, to grow to $1 million. Now let's answer the question. The question was, at what age will you be if this investment began on the day of your birth? The $10,000 was invested at 8% compounded annually. On the day of your birth, how old will you be? Well, if 57.756 years has passed since the day of your birth, you'll be between your 57th and your 58th birthday. You will be 57 years old. So, the answer to the question is you will become a millionaire at age 57.